So I get started. So this is a lecture about grounded cognition. Some of you might have heard that. The people who are in the philosophy or in this introduction course might have heard things about that. Barcelou is the name of that nature. And, many other people. And so it is now really starting to talk about actually real higher cognition. We'll talk about language, some elements of language. And grounded here means linked to sensory motor. Here it will be only to perception. In other words, we actually really look at motor. For instance, if I give you an instruction that you can actually act on it, that's a form of grounding. That you don't just have some statistical representation of what I said to you, but you know what it means in the world. You can act on it. And perception means you can know what I'm talking about. To talk about objects, for instance, here in the room. And so that will make use of the things that we discussed in these last two lectures in December, when we talked about binding and coordinate transforms and things like that. And now we'll make it concrete. And that's why it's fun. We can really see how these things really do cognitive work. So there will be one thing that I will be referring to a lot that I haven't explained yet, which is these sequences of events. There will be neural dynamics that go from state to state, and how that works, I haven't actually explained that, and that is next week's topic. And then we have it all in place. So I'll first say some things about what that means to ground language, and then I'll talk about how we then represent language like things. We're not really talking about speech here or language processing. We're talking about ultimately concepts and conceptual, what we call conceptual structures, so like phrases. And then I'll show exactly how to ground that is linked to perception. And then the highest point is to do that without perception, mental mapping. That's when I'm speaking here about things that you don't really see. Actually, what I'm talking about is abstract stuff, and you still can make sense of it, and do that by making mental images of it, and we'll talk about that. And then sort of the high point perhaps is this nested phrases when we get to properties of language, the systematicity, productivity aspect of language, how we get there. It's just a very elementary form. So this is quite ambitious. It might take a little longer. If any of you needs to run out, you might have to go back to the video later. I think it's good to make it in one sitting because it's all sort of connected. But I'm happy to, if we have a lot of discussion, I'm happy to then let it spill over into the next lecture. Okay, so let's first talk a little bit about grounding of language. So in human communication, in the most elementary sense, evolutionarily earliest sense, humans are talking about their environment, about a lot about themselves, each other, and their environment that is part of the world that is directly perceptually accessible. We talk about a shared environment here, for instance, where those of us who here are present share this room. We can talk about stuff here in this room. For the online folks, it's a bit more difficult. They only have the screen. Maybe I could talk about some part of me that they see. And in fact, there is this notion of shared attention that in communication, very typically, we achieve the function that more than one person or people who communicate attend to the same object in the world or the same event in the world. Very, very typically when I say, oh, where's the remote? And we all know that I'm actually pointing. That's called deictic reference. So pointing, and then you know I'm talking about the remote, and the word remote control is maybe something you know that this is remote control here with the projector. You have some semantic knowledge about that. Therefore, we know what we're talking about. We're all perceptually grounding this, but we're also attending to it. Oh, look, this remote is really cool. Then we have joint attention. You attend to the same object. That's a very important process in communication, and that generalizes to situations where we're not talking about the physical world. When I talk about the terrible crisis in Ukraine, we have joint attention to this abstract concept. It's abstract in the sense it's not currently available on sensory surfaces, but you can link it to experiences, news you heard, maybe some personal experiences. And so we also jointly attend to something of that nature. So this is deeper than just this very concrete scene relative to spatial perception of the scene. But we're starting from that because that's really where we have good neural grounding of those ideas. So this form of this is from Denmark. It's very likely fraud. How do I make this like this? Maybe get a lot of these fraudulent phone calls now. This form of communication about share, things in a shared environment, shared experience, does take other than linguistic dimensions and physical pointing, gaze, a lot of gaze control that I'm looking at something, you're looking at what I'm looking at. That is a mechanism very important in the development of language. Small kids interact with their parents very much by in an embodied form, attending to the same object. It's actually an interesting asymmetry that is typically the kids who select intentionally an object and then the parents that follow and talk about that object. And that's the most successful way to make kids learn new words, but from new objects. It's not actually as efficient if parents say, oh, look, this is a remote. And kids are much less likely to retain that word. And that's part of why we create the environment for kids so that they are interested in stuff around them, and then it will be very good for their learning. So this pointing is a famous one. I think maybe the Latin word is didactic, and that's often referred to as the example of embodiment where you point with a hand or something else. You can do this with a cursor, but of course, it also can take other forms of context. So it's very important. And here in this context, you will easily interpret words to refer to stuff that's in the classroom, right? And maybe it's a teaching situation, or if we are in a sports situation, we will assume that words refer to objects there. I'm not so good at remembering the examples, but a lot of words can have many, many different meanings, and the context plays an important role in that. So these are all non-linguistic components. So we're using this term perceptual grounding, and there's a small community who do that. I have to say it's not a universally shared vocabulary, and there's a little bit of flux here of what terms are used. In linguistics, some people call this targeting. Someone called Talmi has talked a lot about that. Some other people call it referring. And this is the problem in a way is that the situation where you're really linking a phrase to the perceived world is a special case. And a lot of linguists are not so interested in that because they're, for instance, if I tell you a story, then you will understand what I'm talking about. You have some interpretation of that, but it's not directly linked to perception. It would be actually mental mapping where you're trying to build some image of what is currently being said. And so from the linguistic point of view, they are not really focusing so much on this directing to perception. While for our approach, as you can imagine, where we're trying to see the sensory motor grounding of all of those things, that's very important. So we went to this term, and now we're stuck with it. We, meaning as the dynamic field theory kind of community, our approach to cognition. There's another sub-community who actually use it in a related but different way, where people say grounded in the sense of the learning process, actually the evolution of language, how words come about. There's this famous word language game metaphor where some people at Sony Labs developed a couple of robots, or it's actually just cameras, that look at the world and that they, in some sense, talk to each other. It's not really neurally based, it's some kind of AI method. And as they talk to each other, they develop concepts. And then they say that's the grounding of the concepts in the creation of language, or evolution of language. It's quite different, although it is related because it's this link to perceptual experience. Just for clarification, for if you know anything about these terms. So we just mean linking it to your to perception, to attention, I think. Good. So yeah, I already said that. Good. So I will be using, I don't know why this thing here said something, I don't want that. Okay. So I will be using spatial language as the model case around which we'll be doing a lot of work. We'll also briefly look at some movement words. And at the end of the lecture, I'll point out why that's a good choice. It's actually part of a systematic program. It has to do with the metaphor approach to embodied cognition. But for not just take that for granted. And spatial language is particularly interesting. It's this low level, and it's particularly interesting. It brings out a lot of properties that then generalize to a lot of other things. So things like, I'm in this little drawing, the cup is to the right of the green book, right? That would be spatial language, to the right of, behind and above, below, and so on. So you can use that to refer to an object. You also use that a lot in action relating instructions. So you can, if you instruct, you typically talk about objects and moving one thing to another, and spatial language plays a big role in such cases. And
So we would need the grounding and the term to produce the association, right?
To the association between what or of what?
Like, I mean, the is the cup really the like the part of the grounding, or is the cup the term that we want to create
Good.
here, associate?
Good point. So just here. So here we would say the cup is the target object of that phrase, while the book, what was the phrase again? The cup to the right of the green book. Yeah, the book would be the reference object of that phrase. And in fact, we would say that we ground both. We ground everything. We ground we know what the reference object is in the scene, so we would say it's perceptually grounded, and we also hopefully know what the target object is in the scene. And we also, in a way, could actually say ground to the right of that is we could point in the scene to what makes it to be to the right of. We could even point to the spatial area where things are that are to the right of the reference. So in that sense, perceptual grammar just means that all the components of language can be linked to some perceptual and more generally sensory-motor experience, and ultimately to something that you can even construct in your mind. But that process is organized by roles. We call them grammatical roles here, even though these are really, grammatic in the widest sense, right? There's some regular structure to that. So many, for instance, all spatial relations use at least a target object and sometimes a reference object, and there can be, for instance, you can say between, and there are two reference objects. So this is generalizes a little bit. These are, so syntax is a particular way how language forms assign roles like that. So in English, there are these ways of have this to the right of, right? So it's a particular grammatical way of bringing about the assignment of role to different words in the sentence. So I know that the cup is to the right of by virtue of the syntax of English. Then I know that the word before that phrase is the target, and then the word in the accusative is the reference. But in other languages, there are other ways, for instance, flexing the word, or what's the English word for that? Modifying through ending the word to indicate the relationship. And did I answer your question, Sven? Probably yet. Okay. Yeah, so I already hinted at these grammatical roles, I think, when I talked about binding, where it was a question of how we can represent at the level of concepts these things. And we'll come back to that when we now talk about how to ground that. So there is so when you have something like that, right, you do spatial language, there is the actual language use of that, and there is a lot of subtle structure in that. That is, people will typically use spatial relations on the assumption that the reference object is easy to ground or familiar. You know where it is. You might say, oh, it's above the fridge, and you're assuming the fridge is an object that everyone knows where it is. It wouldn't really make so much sense to use a reference object where the grounding of the reference object is very hard, because then you could have gone for the target right away. So there's sometimes this argument, sometimes called the Gricean argument, that there is a sort of a reason why people say things in a certain way. That's their communicative function. In some of the examples we construct, it's always so realistic, because we're constructing examples to point out about some problem. I show something about hypothesis testing. It's violating that a little bit, because in practice you don't really use very difficult to understand language usually, where you have to do a lot of thinking to understand it because of the communicative goal. But we're also using this to put our finger on some forms of higher cognition that are important, like hypothesis testing. So some more jargon here. Interrupt me again anytime if you have some jargon. So we will be talking about grounding as the opposite of describing. We use this for describing. This is, again, not so clear in the literature what that is. So grounding, as I just said, would be some representation of language, like red above green, for instance, would be represented in some form, and I'll explain how that's done in a moment. We call that conceptual structure. That is a term that is used in cognitive science and certain parts of cognitive linguistics, and this will be a trivial case, a single relational phrase. And so, relation above has two arguments, target and reference. That's conceptual structure, where you know which is which role. But then we'll later look at much more complex conceptual structure, like to say the tree that is above the lake is below the, I don't know, something else. And there you really have to know that it's that tree that we talked about that does this thing. That's the same tree that I'm talking about here compared to some other tree that you might have mentioned somewhere else. So we'll get to that. So if you have a sentence, so we're not really talking about how from the rules of language processing you extract the conceptual structure that you know that which concept refers to the target, which refers to the reference and so on. So just assume you have extracted that. And then the process of linking that to perceptual experience, for instance, you have this particular scene, and in that scene you see the red above the green is this thing here. That's what you figure out. That is what we call grounding, and it means ultimately that in some neural representation, we have achieved the attentional selection of the target object. So for instance, here in some representation, this field here, a peak at that location that corresponds to this location here, when that peak has been activated, then I can maybe shift my gaze or could even grasp the object. Then that would be the outcome of perceptually grounding the phrase. Yes, please.
Could you explain what these pictures like target and visual scene? So yes, sorry, just what is represented there.
So this is supposed to be an actual visual scene that you look at, and the model will later gets this as an input. And this would be some fields in that field, in that model that we'll discuss later, that will, for instance, here in this field will be the field in which activation represents the attentional selection of an object. It's a field over location, over that same location space as here in the visual array. So here's, I can say it's retinal topic, you're just fixating. Well, it's another issue of whether it's retinal topic or heliocentric. And these other fields will play some other role that we'll be discussing. And this is a neural representation, a sort of a graphical illustration of the neural representation of conceptual structure, where we'll have discrete neurons. So these are symbolizing individual nodes, and when the bar is up, it means it's activated, and when the bar is down, it's not activated. And we're using color code to indicate what these neurons stand for, and I'll explain that in a while. Does that answer your question? Yeah. Yeah.
In the front representation, the colors indicate the amount of activation.
Yes, exactly. Yeah.
Why is there in the reference where the target is in inhibition, like in the red, like target object? No, the right top.
This one here?
Yeah, wait. Like on the left-hand side, you have the target that has the highest activation,
Yes.
right? And on the reference picture, it has the lowest activation.
Yeah, that's exactly. Yes, yeah. Oh, you mean why there is
Yeah, but
no,
this one is inhibited.
um,
Is it because the target can't be the reference then?
that is interesting observation. I'm not even sure why that's the case. Yeah,
I
I
just
don't
want to
know.
understand why there the activation is even lower than the parts on the left-hand side. Sorry.
I'd have to check
Okay,
that. I don't
sure.
remember. This is just from, I don't even know exactly which variant of the model this is from. We'll look at that architecture and let's maybe try to figure that out. Yeah, these are fairly complex architectures, and I don't always understand everything that's going on there. But Matthias Richter, who did this work, will probably know the answer. Yeah, maybe we can figure it out later. Yeah. So this just make it a little more concrete, but we'll get in. We'll look at it much more concretely. It's just to define the terms. So the opposite direction would be what we call describing. So describing would mean that the architecture that we'll look at gets this input, and then it actually creates that conceptual structure that it is, like says the sentence, except we're not explaining how it actually can make it as an auditory sequence or anything. We're just saying develops that conceptual structure, which would mean it activates, let's say, the red node for target and the green node for reference and the above relation as the spatial relation that it identifies. So this will be describing the scene, right? Taking the scene and describing it. And so one of the features of our model is that it can do both, and that is in cognitive linguistics a real holy grail. So that's why it's important for us. In reality, describing is, of course, a much more complicated thing. So here, so because you have to say what should I describe? What should I talk about? Right? These things are relatively poor, but still you could describe all kinds of things here. You could talk about the other objects or use other relations and so on. This is sometimes called the problem of framing. So what do you talk about? What do you find important? Which angle do you framing here could concretely mean which object do you take as a target versus as a reference? And there you really go into semantics, and maybe you need something like an intention, a communicative intention, what your goal is. Why are you even saying this? And that is actually an interesting problem for us. And my last lecture will be about an intentional agent, where we think a little bit about things like that. Still very, very elementary what we do there. But it's interesting to see what ultimately cognition entails. And you can imagine that actually very little theorizing exists for that. So we have only scratched the surface of that. So this model will do a description just based on salience. So the largest, most strongest contrast object will come up, and it will then look in the neighborhood for something else and then talk about the relation. Yes, please.
I find the representation very interesting, and I asked myself, like in this example, we have one specific target and one specific reference. What if you would, for example, say the red ball above the ball, for example, because it has ambiguity, right? Because
Yes.
we have two red balls and two balls below this. How would that be represented?
In this example, is chosen so that there is another red target, and that would mean, in the Gaussian sense, you might need you would use spatial language, because you would not have it would be not enough to use just the feature value. While if you don't have to do that, you typically would actually do that, just use the feature description itself. And ambiguous situations where there would be multiple solutions are interesting. We'll come to that. We're interested in that exactly because it's an interesting theoretical challenge. It's a little bit contradictory to Gaussian thinking, because people usually don't on purpose say ambiguous things. So if they see that it's not clear which object they mean, they might actually use a description that makes it unique, except by error, let's say. But it's still interesting to figure out how to deal with it. Yes, and we do have some ways to deal with it. Of course,
But if
truly ambiguous, if there are two objects that meet the description, then there is no solution to that. The system might just select one of those. Yes, I think this might be talking. Yeah.
like assuming that there's other objects which have higher salience, wouldn't that lead to an anchoring problem where for example, the color could be falsely interpreted if we pay attention to the lady in the red dress, to
Yes.
use a figure of speech?
Yes, so in grounding, when you are really looking for what is described, what is in the phrase, there can be that problem. Actually, the example I'll show you later has that problem that the salience attracts you to a certain interpretation, and that turns out to be wrong. And then we have to deal with how to overcome that. In describing, then we would just go for whatever. So we don't really have any interesting solutions. So it would just describe something salient, right? And if you want to overcome that, you'd have to have other ways of creating communicative intentions.
Thank you.
It's kind of interesting how even this very trivial stuff, already opens cans of, what do you call that? Cans of worms, perhaps, right? Or what is, there's a metaphor, which I forgot now. Yeah, can of worms, right? Isn't it? Yeah. That's very typical in cognitive linguistics. And so we actually found, as we're doing this work, we tried to look for psychophysics that would constrain the theorizing. And it's not so easy to come by. A lot of this work is very different in nature, often more interpretive and speculative in a way. We have I'll refer to a few psychophysical constraints, but there are not a lot. Okay, that's just the terms. So the first point I made. And now we'll link them to neurodynamics. Okay. Good. So I'll next talk about how to represent conceptual structure. And again, do this in a somewhat microscopic way. So one thing is concepts. So the concepts are a huge kind of forms, right? As I think many of you might be aware. So what we're doing ultimately is a trivial form of prototype theory kind of concepts. That is, we would say concepts are just one step removed from perceptually grounded stuff. So for instance, if I have a color concept, it means that I have an underlying color field that would be linked to ultimately a sensor. In this way, like you remember extracting the color dimension. If you have color-tuned neurons and you just extract the color, and you have a peak that indicates just the color of some object. And now the idea would be that you have some nodes that represent certain ranges of color. Now, if we, in a naive sense, it would be, if it's hue space, it would be just localized in hue space. In reality, it might be more complex, might have mixture of colors, and they get some name that becomes a concept. So it's categorical in nature, but it is linked to the sensory surface. So the node, when it becomes activated, is capable of biasing the color system to select objects of that color. And that will be guiding visual search. I have hinted, cued selection would work this way. And conversely, if you just look at a scene and there's an object like that, then the color node could become activated. That's how you would classify an object as having a certain color. And there's a lot of work about color concepts. It's actually a very nice, experimentally nice example where you can work nicely with that. A lot of developmental work. I have the life experience with my grandchild who now uses very confidently the color concepts. It's an interesting wrinkle, for instance, that kids often know the word color before they know the names of all the colors, which is kind of surprising, perhaps. My granddaughter apparently is very interested in lila. And she talks about lila always. Like your hair, exactly. Which she's bilingual, so it's actually also interesting in that way. Yeah, so that's very simple forms. So it's bidirectional connections. It's not very deep. So just to hint, one can do this deeper, just a plug. So of course, other concepts are much more not a simple feature dimension. For instance, if you know a BMW, how do you know that a car is a BMW? Well, actually, probably by this logo, but I don't know, some other better example, I don't know, an anchor, like you know what an anchor is, and what it looks like, and its function, and so on. And so the link to perceptual experience is much more complex. And so one aspect of complexity is that there would be a lot of specific features that characterize this object. And we know that, for instance, here, these deep networks, for instance, are able to, we are actually able to train them to extract features like that. So the features that are good for classification. And one can actually really link that to concepts of this nature. So one of our models, for instance, has a deep network here, which we then, through some learning process, can associate with localized representations of the category. So that's the important thing. When ultimately we need a node that stands for that category, and that node is embedded in our thinking, that it is self-excitatory and inhibits all other nodes within a certain field. So it's nodes, but they are still parts of, in a sense, of a field that doesn't have metric dimensions, in that they compete with all the other nodes, and you just select one color, not two or three at the same time, or one category. And that is the part that is actually not done in conventional neural networks. You might know that conventional neural networks might perform categorization, but then the decision is made by just looking where the maximum activation is. It's typically an algorithm that's outside the neural framework that does that. It's actually a piece of code that says when you're going to look, which is the winner, for instance, or have some probabilistic way of doing that, of saying I have a, for instance, I have a ranking list of most probable choices, and then have some algorithm of taking the highest ranked choice. And so we can link this sort of logic to neural dynamics without using any algorithm. I'm going to the next one. There are also, of course, other kinds of concepts, like these relational concepts and verbs. So you could say these concepts I talked so far about are sort of noun type or adjective type. They are sort of property or object kind of concepts. And then you have verb-like or relational objects, and those have arguments typically. You have an agent and maybe an object. You might have a tool that the action is done with. And we'll come to that, how the arguments work. I'll come to that. Here's just an illustration of such concepts, how they could be neurally done. So for instance, if you have a node for to the right of, you can imagine that this could mean that you have some kind of synaptic pattern that looks like this. So here the color code indicates some sort of synaptic coupling strength, so that the synapses here, so you're looking at how this node projects onto some spatial representation. We'll have to see which one. And in that spatial representation, anything that falls into this part has excitatory input to this node, and anything that falls into this part has no input to this node. So you could imagine if you do that and you have an input that's here, then this to the right of will go on, and you have an input that falls here, it won't go on. And that's kind of intuitive that this would then therefore be sensitive to stuff that is to the right of the center of that space. And that would be a to the right of node, to the left of, below, and so on. And actually, we're completely modeling these synaptic patterns based on psychophysics, so I'll come to that. There's some other gymnastics we have to do, there's some coordinate transform stuff to make that actually work. And you can imagine you can have more complicated concepts like that. For instance, we do the simple action words like move to or move away or move in a certain direction, and then you can do this in a movement space of extracting the movement direction as a feature. Okay. So in this binding to role, I did actually previously explain some aspect of that in I think the last lecture I did in December. So here I'll just say that when you have these concepts now, you remember I talked about the need to associate, to somehow bind the concept to its role. That's the role filler binding problem. So for instance, I have to say that the green here is a target and the red here is a reference in this phrase, right? To the right of red. And in a conceptual structure, I have to represent that. And the notion was that we would have different copies, in a sense, of the concept. For instance, the red concept would have a copy for red as reference and for red as target. That is like anatomical binding, that all possible combinations are represented. And similar for green. And therefore, the phrase, the green to the right of the red, could be represented by activating the red node for reference and the green node for target. And this still would be grounded. You know, the notion would be that all red nodes, independent of the grammatical role, would be grounded. So they share this connection. You could say, think that when you learn the concept, you just activate all of those nodes, and the heavy connection is from all of those nodes. There be a joint representation of object involved. That's one of the solutions to the binding. It's not catastrophic. You could always think if you do that, joint representation always have this risk that you need millions of neurons for every combination. It's not so difficult because you would still say every concept just needs a small number of roles, because we're assuming that these grammatical roles are quite limited in number. Target reference, tool, agent, something like location, much more. Yes, please.
So if I understand it, so the colors, for example, are represented by the strengths of the activation of certain nodes in the feature field. But it seems like the spatial relations, like right off, left off, are literally represented as special relations between these nodes. So like when we speak about relational topic map, for example, so the space literally involves the space. Do I correctly represent it? So I understand it.
So red here and other dimensions like that, like movement direction, would be feature spaces, right? In this original sense that we talked, that you have different features represent separately, like color features, and maybe you can talk about size as a feature, the big object, the small object, and then you could have a shape feature and things like that. And abstractly speaking, space is also a feature. So it's just often combined through this binding idea with other features. But you could say there's spatial features. I mean, space as a feature, and therefore the relation would be a spatial concept that's defined in that space. And it just has these particular shapes. I mean, in the color, we just arbitrarily assumed here that these colors have Gaussian type perceptive fields in hue space, which isn't really psychophysically realistic. They are more varied. And we assumed, some of them have these particular shapes, which we can figure out for some concepts. But you can see, for instance, if you do something like inside of or between, then it becomes more complex. We've actually done things like that. So there are all kinds of spatial concepts like that. And now think about shape concepts. You could say it's curvy or it's smooth or things like that. So then the feature representation of that could become quite complex. And actually, some of these deep networks develop features that sometimes don't have names. Just you can analyze it. It's in the early layers of these deep networks develop features, which we actually use in our work to attach to concepts. And so they're not always, these could be like a corner, could be a feature.
This is just a coincidence here. The red is literally right of the green. It's not how it's encoded. It's just here like this. Like the green.
I mean, our ambition,
yeah. But that's not how it's really represented in this feature field.
So I haven't really explained yet how we know that. So currently, let's say in this one, I wonder if I have a good figure for that here. Not yet, but we'll come to figures like that. So in this simplest version, we just have a whole battery of nodes. Some of those are feature nodes, like these red, and they have these roles. So I can activate the red reference and the green target node, for instance. And then somewhere I have a to the left of node. And then that pattern of activation among these nodes represents the phrase. And so, for instance, there is a problem that only one phrase at a time, right? Because if you have multiple phrases activated at the same time, then you have a binding problem. You don't know, is the red reference, is it of that relation or of the other relation? And that's when we talk about nested phrases. We'll have to exactly address that problem. Yeah. So we'll come to that. Yeah, it's very pedestrian how we do this compared to linguists. So always start with the complicated stuff. We start with the simple stuff. We're physicists doing simple stuff. Okay. yeah, this will become more alive in a moment. But before I go there, I need to talk about the grounding of relations to make that concrete. This will be a single relation. So this is the slide I had earlier, and that's sort of an overview of the processes that we need. And then I'll show you actually a few slides here from an older model where we can understand this very easily, and then I'll show you a complete one. So earlier I said, well, we represent concepts here, and that I don't have on this slide. I'll show it in the next moment. We have some way of how red and green in these two roles are activated, that with the conceptual structure. And then what we'll arrange is that then these target nodes project onto a spatial field that is for target stuff. And the reference nodes project onto a spatial field that is for reference stuff, a separate field, attentional spatial field. And then we'll have a coordinate transform. That's one of these ones that we discussed last year, that represents the target space centered in the reference object. So this would be like gaze. The steering dimension is where the reference object is. And so we're representing this centered in that. So for instance, here, this target that's sort of in the middle of this space ends up being, if the reference is here on the left, then this target ends up being to the right of that, right? So you're centering it here. It's the, I don't know if that's the input to that. It might be the input. So red is the reference. So here on the left, right, that's red. And if you're representing this, you're centered in that, then you see the green will be pretty much on the right. That's why the green ends up being here. Well, in the original picture is more in the center. So this is the normal coordinate transform that we looked at earlier. The interesting thing is this works even if you haven't yet selected the reference. It's a recurrent dynamic system, so it can sort of converge to this, even though initially don't even know where the reference object is. This is the magic. But if you assume you know it, then it's a straightforward transformation like that. And so once we've done that, these pattern forms of coupling will work, because now the reference object is in the center of this receptive field. And so we can apply any of those here and then get, like select this object, this target object, because it's in the right cone. And if there was another object that was here in this cone, it wouldn't be selected. That's roughly how the cone works. I'll show you this in more detail in a moment. So this coordinate transform is a special thing for us. And it essentially means that we can get away with just having learned the concept. So the concept is just neurally represented by this synaptic pattern. We just designed it, but you can learn it by having learning very easily. But we only have one such concept in our mind. So you have one concept of to the right of. If you didn't do the coordinate transform, you would have to learn a concept of to the right of for every location in the visual array. Maybe a retinal array or allocentrically or whatever you do. You would have to be able to say something is to the right of here or there. And that is literally what deep networks do. So deep networks get this successive training and they get examples of to the right of for every location. And for every relation, it's like that. They actually have this principle of weight sharing. I don't know if you know that, where they just learn it in one part and then they copy these weights across the whole thing. So that they have a little shortcut of not having to learn so much. But it's still that kind of idea. And that's, of course, totally non-biological. And this is what we propose is true. And that actually is connected, as you remember, to the attentional bottleneck. That is actually the reason why we have an attentional bottleneck. So that's conceptually how it works. Let's take here this old example. This is an example where we didn't do it autonomously. And so we had some external way of guiding this. And next week, I'll explain exactly how the autonomy works. But it kind of sort of easier to understand. So here, this will be the visual scene. And essentially, there are three things that you need to do this, right? So you need to bring objects, to select them attentionally, according to the phrase that you have. And then you need this coordinate transform I was just talking about. And you need to apply the relational operator to these selected objects. So here, for instance, you have these concept nodes, red, green, blue. They are connected to the color dimension of a 3D field. So you have a spatial field, and the third dimension is color. We had that one last week. And so one slice is red, one slice is green, and one slice is blue. It's just not, it's a Gaussian. This is a little band, and it's like a slice with a little thickness. So that's how, so here we're just plotting these three slices. So that's the grounding of these color concepts. And here the grammatical role wasn't yet represented in this old version by a discrete node. It's just by some selection boost. So for instance, if I set green as a node and I boost the target field, that represents that it's green as a target. And if I then boost later blue and reference, that represents blue as a reference. And here I have these spatial nodes. There's two for some reason, but ignore that. So spatial nodes, and they are connected through the synaptic pattern to this object-centered field with these patterns that I showed you. And the coordinations form here makes that's centered in the reference object. So let's go through how this does the grounding of a phrase. So the phrase is not standing here, it's just in the process, sort of fed step by step, and what the autonomous one then does that by itself. So here, for instance, you initially set the node of green as a target, and that is expressed here by giving, activating that node, and that node gives a boost to the red slice. That's analogous to the ridge, right, in a 2D picture, and in 3D pictures, a boost to entire slice. So anything that is green will have a chance to build a peak, and here this thing here will build a peak, while the other ones don't. And all of these spatial fields, the entire 3D field is connected to both the spatial target field and the spatial reference field. But only the target field got that boost from the roll, and therefore only this projection is effective. And this is also an interesting property of dynamic field theory, that you can have coupling in an architecture, but you can sort of select the coupling that is currently active by enabling a target, the target of the coupling. It also happens to be the target field here, to build peaks or not. And that's controlled by boost. Remember, detection instability, you have to reach thresholds. So if you give a boost, you might be able to build peaks. If you don't give a boost, or you even give an inhibitory input, might not be able to build peaks. So even though both fields receive that input, this field can build peaks, but this one can. Therefore, effectively, you have selected this coupling. So here, the object at center will be selected as a target object. A moment later, you give, I have that slide double, I don't know why. A moment later, you give it red as a reference, and then again, the red object will build a peak, and because of this boost, that peak will go into this object here. And you already see this field here is now a representation of this target centered in this reference. So, the reference very much to the left. So I think here's the reference object. So the target's to the right of it. Now you see that to the right of already get some input here. And then I think in the last step, we boost this here so that now they're able to make a selective decision, and that will answer to the right of. This is actually doing something we did then, like in the answers. It doesn't get the relation, it actually answers what it describes, it says what the relation is. We just use this for that illustration. So let's look, these are some videos that illustrate this is really looking for grounding the phrase. So the green object, no, actually this is looking for the answer of what the relation is. So it's mixing grounding and describing. Maybe not so pedagogically clever that I'm using this, but in the past we actually mixed that from the very start. It's just a very nice movie, so let's do that again. So we're giving it green and as a, I think as a target, and then we give it red as a reference. And now it actually figures itself out that it's to the right of. Is that right? Yeah, that's right. Okay. And here we're giving it blue and above as an object, and that actually now the coupling the opposite direction works. It figures out that that is the red object. So this, it has the reference object can actually transform, and see there's no object here yet, but the reverse projection enables it now in the recurrent loop to select the matching object.
So
Yes.
what is like lower ones? What do they show? Special nodes and objects and
Yeah, so yeah, actually I now see this is not very clever in terms of systematicity in teaching, because I'm using now an older model that mixed things that we now distinguished a bit more carefully. So here we're actually using the model to not just ground, but actually to answer with a categorical answer. So when I say which object is above the blue object, I'm actually answering it's the red one. And in the end, it will be the red node that goes on up there. You see the red node goes on. And so it uses really this multi-directional way of how the coupling works. So what I'm putting in is that the blue object is the reference object. So I'm giving a blue node activated there on top, right? That's the input. I activate the blue node, and I give a boost to the reference field. And that expresses that blue is a reference. And now I'm, the rest is autonomous. Now it just feels the just in the reference field. And now I'm just boosting both this field and the target field. And it will be, no, sorry, I switched to the other movie, this one here. So it will now, so it has found here the reference object. You see the peak here in the reference object. And now it will find the target object because, so no, sorry. I'm also setting above. I'm actually activating above from the outside. I'm telling it's a relationship of above that reference object. So this was from the outside. And if I've done that from the outside somewhere here, I'm setting it here, yeah. Then in this field, the above operator, you see the shading comes from that operator. The above operator will now, it gets some kind of sub-threshold input from this field, and this sort of, in recurrent connectivity, it now emerges to build a peak that is up here in this domain, which is the red peak, while the green peak, for instance, doesn't go through because it doesn't fall into this part of the kernel. And so it finds the object that's in this part of the kernel here in this above, that happens to be this object. And then it actually looks up its color, because this is fed back into these layers. And this location is that location, and that location is red. And so that feeds into the red nodes. So that's how the system ultimately answers to the red. Yeah. So this is in a way more advanced than our latest models. We don't mix things this way. When you mix things this way, this is actually inference, right? Because you're doing a grounding process, and then you're doing some thinking, you build some conceptual structure, right? That would be inference. Yes.
Wouldn't the blue anchor initially inhibit the red?
Yes. So when I see the blue was deactivated here, if I have blue and red at the same time, then there would be two slices and they would compete.
Okay.
Well, I do it one at a time. And that's part of the autonomy to get that to organize itself, that it does this sequentially correctly. And I'm only discussing next week how that works. It's the conditional satisfaction stuff. So that's why initially we did it with an external schedule. And there's another one we don't have. So and this is the radical thing. In this old version, we could do that. Just green, right? We're just giving green as a target, and that it can do everything else autonomously. So here green was, targets up there, and the target field gets boosted. You put the green here in the center. This is the green thing. Oh, sorry. Let's do that again. No, yeah, this one. Does it run? So you got the green here, and now it everything else is boosted. This is boosted, and that is boosted, and it then selects one of these, and this is just posterior. So it selects the blue one because that's larger, and selects to the right of, I guess. And so it gives the answer that the green is to the right of the blue. Okay, that's so describing, right? So it's just saying in space. That was the old model that already, did something related. Yeah.
Why are these objects like in color nodes, why do they move up and down? If because if they move, it seems that the position is changing.
Oh, the moving, sorry, this is just a way of illustrating. These are nodes, right? Discrete nodes, and the level of this dot just indicates the level of activation of that node. So this is zero, this is positive activation, negative activation. It's a different way of representing. Yeah. Sorry, I should have said that. Yeah. So familiar with these plots that if I guess, then I have to explain that. Yeah. Good. Yeah. So this is, essentially we then systematized this approach. This model was actually this first foray into this, actually the second, some complicated history, but the one where we, so more than 10 years ago, where we tried to do some psychophysics. So for instance, some data where people are asked to rate how good an example of above or to the left of also a certain scene is. And I have an object where, let's say, I don't remember exactly, I think the L is some other word for target. I don't remember what it was called. And then you have to say, is this a good example of above? And that's a very good example of above. And this is almost still a good example of above. But for instance, when there is a distractor object here, then people say this is not so much above. And that's why this is lower, and a couple of complications like that. And we were able to fit this, that's our model. And our model was the amount of input to that corresponding node that we compared then to that rating. So this is very typical. People do this rating. Frankly, I don't think these rating data are so strong. And actually, it's not a huge constraint on the models. Mostly the kernel size that is right. And I mean, it's a kind of cool thing that because we do have a representation of the distractor, and for instance, has a different feature value, and we can really get these distractor effects right. So the only model that does that as a process model. Still, it's not a huge constraint, I would say, for our kind of model. Good. So with the modern version, this was published only 3 years ago. That is this model here. And so, and it doesn't even have some details that are not shown. So this is, I use this opportunity to clarify this because this is now the topic. When you go to higher cognition, right? What do you expect? It's not going to be harmonic oscillator, right? So it is more complex, and the excuse is that there are a lot of subsystems. I'll take you through those that are actually not freely invented, that are constrained by other fields. So for instance, we have a visual search architecture in there, and we have a visual search model that is compared to data is actually more complex than this. It's a simplified version of visual search. And so we account for that. And we have, for instance, a model that accounts for visual working memory. And I have some psychophysics that's explained with that. And we have a representation of that here. And then, in a way, it's a component that is independently verified in a different domain, right? So it's not all freely invented. But there is still, it's still very complex. So I'll take you through this sort of just categorically, so that to show you that it's not much, it's essentially what I just showed you in the simplified version, and it's just a bit more systematic. So for instance, here are the color concepts. There are color nodes, and the role, there are 2 copies. So this is the, actually don't remember if it's the reference of the target. This is the reference, right? So this is the reference node, and that is the version as a target node. The grammatical dimension shows up in this way. So they are grounded by projecting onto a color dimension. These are fields along color. There are two nodes here, and there are two fields here, and so on. That has to do with the autonomy. That has to do with what we call conditional satisfaction. We'll get that next week. So that's something that distinguishes between you having the goal of grounding something red and having achieved it. When you've achieved it, you're satisfied. Then that frees something else to then do the next step. You're done with that intention. So that's how we get autonomy. And similar here, all these multiple copies are always about this autonomous process. Here this is a model that actually also grounds motion concepts like moving to the red or moving away from the red and so on. And so this is a movement field. These are different vectors here that show different directions of movement. We really extract the movement from the visual array with a motion detector. And I happen to work in motion detection in some other fields. So we took models of motion detection, so called counterchange model, as the feature input to that field. So that's an example of really having psychophysically evaluated subsystems here that work because they account for some other data. So here's, for instance, a node for leftward motion and rightward motion. And there's another version, is a toward in the way node. Here are the relational concepts. So this variant has the toward and the way, and then it has the spatial relations. And this is in a different field. The toward and the way looks similar, but it's in the motion field. And then there are coordinate transforms. It's a bit more complex. So the coordinate transforms we just talked about, where we center the field in the reference object. And the two are just plotted because the two directions are plotted as separate field, just because in the CEDA code, it's two different things. And the bidirection means there is one direction, and then there's another line for the other direction. And so you have two copies of that, but it's the same mechanism. Sorry, I clicked on something. And then here, there is an analogous coordinate transform for the movement direction. And that's actually something I skipped here in this version of the class. Something very interesting about spatial relations in that they have absolute reference frame versus relative reference frame. You know, some people say, north and south, for instance, or toward the mountain or toward the valley. And something when you're a skier, for instance, some people use language like that. Like you said, your back ski in German, your mountain ski. The ski that's toward the upside, right? You want to use that differently than the Tal ski, the one that's pointing downwards. There would be an example of an absolute frame, so in the outer system. While when I say, for instance, something is, let's say here the Wi-Fi system there is to the left, or the router is to the left of the outlet, then that is it's a reference frame that's relative, right? That is not so that is relative to that reference object. And there are, with respect to motion, there are that's particular, you have that example when you go take the regional training, they say the door on the right in the direction of travel, right? So that will be an example of where the reference frame is anchored in one of the objects. So it has particular directionality by movement. And that's exactly what this is. So when you use toward or away, then you want to rotate any movement direction along an axis toward the object. And then you say motion is transforms. The motion around the world is just an absolute motion. Now has to be rotated relative to a particular axis from one object to another object. And then if it is in that direction, you would say it's toward, and if it's, for instance, the opposite direction, you would say it's away. And that's done another rotation coordinate.
Out of curiosity,
yeah.
Where would auditory data be integrated? Like if you have a very loud noise, would that then just determine the rotation from the position of the self, or?
Yeah, so auditory data I would say what I can meaningfully answer is auditory sensory information is very relevant to spatial orientation, because auditory data, as I mentioned in the other course yesterday, is more about space, but about the spatial position of the source of sound. And that can easily be integrated into spatial representations like that. For instance, if you say the speaker, comes from the window, then you're referring to something spatial that you know where this window is, and then you say, the sound comes from the window, let's say, or comes from the door, from this ventilator. So what one would extract from the auditory system is a spatial map of something like source. That will be some intensity estimate, or you have some other, like maybe you even, like here we have this annoying noise, which I think might be the projector. And we can actually classify that sound as projector sound versus my voice, let's say. And therefore, you're able to, in a sense, visually or spatially find the projector by being able to classify the sound as projector sound. And then you can filter out that sound that will be a ridge or a slice into a 3D spatial perception, actually 2D spatial perception. And you'll be able to find out where that source of noise is that you have classified as projector noise. And so that will how it would be naturally integrated. Other things you can of course think, like a musician would talk about pitch and maybe I don't know, something like the drums are ahead of the trumpet or something. If the drummer hit the drum too early. And it's not categorical. You can imagine how that could work, right? You would, again, have to be able to categorically recognize the drum as a drum, the trumpet as a trumpet. Now you would have to have, there would be relations, for instance, temporal relations of how I'm saying, something is before something else and so on, which is its own field, actually, how to do that. But sort of analogous to space, you would have some way of having a representation of spatial ordering. And then you could use relations for that. We don't build concretely models like that, but I think it's quite closely analogous.
Yeah, I can see that. I was just wondering at which level this would interfere, if any.
Interfere, I think
Yes.
it would be more it would be integrated, right? Our language.
Yes,
so when we're
like,
talking about conceptually about the world, it's actually multimodal. This is actually a real debate. Bartholomew, those who know this work, talked about perceptual symbol systems because he thought that language was not necessarily amodal. Well, the classical view is amodal. That is, it doesn't matter what the sensory source of information is. You're talking about the projector. That's an object, and the term projector entails all properties of it, so that it looks a certain way, it sounds a certain way, it has a certain function, it might have some other semantic connections. And Bartholomew was actually calling that into doubt. So and there's a whole literature on that, and saying, well, it's actually not reasonable to assume that we have these abstract conceptual systems. They are tightly tied to their perceptual manifestation. So there is the printer, the projector as a visual object, and there's a projector as a sound object, and so on. And that is actually consistent with what we're doing, in that we would have, a sensory source about sound to localize the projector, and a sensory source that's visual about the projector. But there is integration, and that the integration would come ultimately from a concept node that would project both to the auditory features and the sound features. So in our language, there isn't really, that's not really a problem. And that's, one could say that the concepts we're talking about are always grounded or groundable, because they have these projections to the feature spaces. So we don't actually have a symbol grounding problem, right? The original thought was there are the symbols in your mind, like projector is a symbol. And then you have to ground it by saying, oh, this thing, the projector, has these properties, or something that you have to add. And we'll say, no, it's actually the other way around. You have the sensory dimensions first, and from the experience, you can then maybe categorize it.
I see. Thank you.
And maybe Okay. Yeah, it looks like I'm going to have to split that lecture. Okay. So coordinate transforms. And then the role filler binding, I think I already had that, right? Oh, this was just a concept here, and then this just points to the fact that that there are these two verbs that already explained that. And these roles control the grounding process here. So what you make sure is that when you have a reference node active, then that projects into this here, so it gives this a boost. And when you have a target active, it gives that a boost, right? So that's just like in the other version. That's really all there is. I have the sense that I didn't show here this part, which is really just the 3D arrays of feature space fields that I think we are familiar with from the other lecture here on the left. I didn't seem to have highlighted these, but that's then everything that is in here. So I didn't explain this yet. This has to do with the sequence generation that comes next week. Okay, so here are a few examples. So this is why does it not run? Do I have to click here? Yeah, okay. So here, what's to the right of green? This is actually, again, where it gives an answer. It's the same thing, it gives an answer, conceptual answer, it says red, I think, in the end. Some red node goes on here. This node, I think, should go on at some point, hopefully. Last moment. Yeah, there it goes on, right? And so this is just the autonomous version of what I just showed you. So the cool thing is that this really just is the system running continuous time, and these different steps emerge from the instability. So that's what I'll explain next week, how that can happen. How can a system like that make steps of thinking in a way? Yeah. But other than that, it's the same as I just showed you. And we don't have to go through that example. So it's just another one here. And this is where it actually really finds the orange. So this is an interesting, no, let's not do that. So this is the example where we do this for motion relations. And in fact, this is where it's doing this, it can do both describing and grounding. So when you do grounding, you give this the phrase. So for instance, here, the phrase is encoded in these nodes. So this is the red node. Again, this is the vertical position, is just how activated it is. So the red node is on as a target. And I think this is like to the left, or moving to the left here. That is set. The red moving, no, to the right. There must be an arrow that goes to the right. Apparently, it's like very pixelated. Arrow to the right. So this encodes that phrase. And this was the movie it was played, so it must be this thing. It's moving to the right. And so actually, it's this movie that it gets here. See, the red one seems to be moving to. No, actually, there's a different movie here. This thing moves to the right, and that thing moves to the left. See, the top one moves to the right, the other one moves to the left. So it's supposed to be able to find out that it's this object. And it does that. And just to illustrate that, here is the representation, I think, of the attentional field that gets input from motion. So when you say rightward motion, so here you see the different motion directions. It's just a 1D slice, especially just 1D. So the different motion directions, and so the motion to the right of gives you this ridge here. And then only one object overlaps with that ridge, and that's how you select the one that's moving to the right. That sort of visual search for an object that moves to the right. So it can do that. It ultimately finds it's that red thing that it does, and it's kind of cool because it actually does move. So you intentionally select, but you also track it.
So this down one that's movement, and this like vertical one.
So in this case, there are two red objects. So only the red objects have any chance to win because you boost only red. And one is moving to the right and the other is moving to the left, and it can select the one that's moving to the right, which is the top one here, this one. Yeah. It's just a demo that we can, and we did a lot of batteries of demos like that. So this is really a process model, right? That is, it really does that. It doesn't just like say something, how likely it was or anything like that. It makes a decision itself. And I show this because it can also do the reverse. That is, you can put a movie into this without any of these nodes activated. There seem to be two activated. I don't know what those mean. I think they're just boosted and you have to select one of those two. Yeah, that gives the system the bias to look for movement. So these are the two movements, toward and away, and everything else is not activated. And then the system gets into the movie where the red moves to the green. See, the red moves toward the green and the blue one doesn't move. And then it figures that out. So in the end, it has activated green as reference and red as target, and then it has selected toward and not away. It also knows which objects we're talking about right now. And exactly how that works. Now here's by this boost of the movement nodes, it only looks for moving stuff. So it's boosts the sales of it. And here, and the last thing is this, what we initially talked about, autonomous hypothesis testing. The red cup is to the left of the green cup, or you say, or that is to the left of the green cup, right? And that is a case where, with a little thinking, you see that it's this one, because there is nothing to the left of that one, so it doesn't work. This is not very Gaussian, because I think people would say that, right? This is a bit stupid. But it's just, just a theoretical challenge. And here's a challenge because this one is larger, so our system will select this one first as a potential reference object, and then we have to solve the problem of getting rid of that. That is what we call hypothesis testing. And that's really the problem that we try to solve here. And we have what we call a condition of dissatisfaction for that, which I only will explain next week. So here, for instance, just take you through the sequence. It will select, this is the reference field, it will select this one first because it's all just by larger input, closely larger input. And then we have some way of, so then it actually looks for a possible red object that will be to the left of it. So these are the candidates here for that. And then it has some way of finding out that that doesn't work. Like, you see, this will be the operator, and it doesn't really work. And that is the condition of dissatisfaction that I'm not explaining so far. And then it will suppress the selection. And in fact, you will have, there's an inhibition of return. So it will not actually reactivate that location. And then ultimately it finds the right target and the right reference object, which will be this one, right? That's the right reference object, and the target would be, yes, must be the top left. But this is in the reference frame where it's centered on that. So this here is actually that red cup in the frame centered on that. That's why it's here just a little bit to the left of it. And the details of that were engineered to be like that, right? That's just to show we can do that. Yeah, that's a version of that that's autonomous. So here, it's the same thing, except it's with screwdrivers for some reason. We have another distractor here, and this is the condition of dissatisfaction, which is the mirror image of that, and it does that. That's all I can say. Good.
So this is an example how top-down attention could bias certain things. Yes.
Yes. Yeah. And in fact, that is in a way always the case. That is, we have this one case where we're now trivially using salience to select something for description, but all our visual cognition work, and I've only shown a very small part of it, is actually top-down. And visual search, when you're looking for something specific, is top-down. The bottom-up salience is actually a problem, because it's only useful if you're talking about the most salient thing. But if you're not doing that, then it's always a problem, right? You always have to counteract salience, and that's a major topic in that field. And we have a very good Raoul Grieben, whom he corrected some of the exercises. We haven't met him. He is actually now the pope of that, and done a very huge model of that. It accounts for a lot of data. that solves exactly that problem, how you deal with this trade-off between bottom-up salience that is the letters and top-down.
Thank you.
All these perfects top-down processes.
I think I didn't quite understand the question. Can you say it
I
again?
don't think I understood how these perfects top-down processes.
Well, so in a sense that, for instance, so here, this is actually a bad example. Well, it's partly good because here, the difference between selecting this cup and that cup is actually salience, right? There will be, in a way there, you see the salience does contribute, but the fact that you're not taking this one, for instance, is because you're looking for a green reference object here. And so the fact that you're then selecting this one is because you're guided top down by looking only for green stuff. So that's top down in that sense, right? The selection decision is based on a queue. It's queued selection. And I mean, in visual search is maybe most apparent after some reflection. Again, this is confusing because there's still some freedom of selection. But in visual search, I haven't really talked about visual search here, and I'm not going to, it's too complicated. But visual search is the first thing every intentional act entails, right? If you want to achieve something, you first have to look at the things that you want to achieve something about, typically objects, maybe it's a tool or whatever it is. First select that, even mentally, if you do a pure, and we'll come to mental in a moment. When you're talking about something, the first thing is you have to create a neural representation of that, bring that into the foreground. And that is some form of queue selection, because it's not something arbitrary you bring into your foreground. It is the thing that you are thinking about. That's the queue you have. Okay. So this is a lot of stuff in one lecture, right? But this is a lecture that really gives the flavor of things. And this is not something you're supposed to remember, right? Good. So I'll do a mental mapping, and that will be the last one. Yeah.
Based on a mental cue, which you only represent mentally, then it's not really a visual stimulus that goes like the
Yes.
initial thing. So it wouldn't be just visual cues, it would also be mental representation.
Exactly. Yes. And exactly that's what I will be talking about now. That's mental mapping. Exactly. So and that's really the step to get rid of now this direct link to sensory motor surface, but we're hypothesizing that the way you do that is still informed by that is you're still doing that, representing things this way, but you're representing it, the activation is not input driven, it's actually driven now by these binding processes. And that's what this example is about. So there's a whole field of that, and this was our entry point in this field. We're very interested now in more stuff like that. So in this field, people give you some propositions. For instance, we did this with colors here for the model, but typically you do it actually with categories. I think the data, this is from Knopf's lab in Gießen, where they did this, like, I think with the parking garage, and it's like you say the Porsche is not to the right of the Volkswagen, and then the Opel is in front of the Porsche. And, and it's actually easier if you do it with categories, these red and so on. That's a bit confusing, and we just did it because we can ground these better. In the meantime, we can actually also do categories, but at the time we couldn't really. I mean, abstract categories like car brands. So if you get these sentences, you really have to concentrate hard to get that right. And it is a cognitively demanding task. You have to build a mental map, actually. It's what you do. So you get a sequence of these sentences, and then you're asked something, where is the blue relative to something else? And there is a whole literature about that. This has to do with essentially logical thinking or inference, how people do that. And there's someone called Johnson Laird, famous for that. Have you heard about him? So Knauf actually did his postdoc with Johnson Laird. He's been inspired by them. They published a lot together. And so there is a view out there that when we are using logic, seemingly, I'll give you a couple of, forgot the term using predicates, right? These predicates, yeah. A few predicates, and then you can, answer a question, infer something. That the way you do that is actually mentally map situation. You create an example situation of what these predicates mean. We would say ground, mental map, and I'll show you how that works. And then you essentially use that map to ground the question and answer it. And that's what our model will do. And the kind of evidence they use to show that you do that is essentially that there are certain regularities. For instance, if there are multiple ways of how to map that might lead to different outcomes, then people typically take longer to answer the question of a higher error rate, or even the kinds of errors they make reflect that one of the variants of this maps. And here, for instance, is an example of this nature where you can say things, let's say, if you have the Audi to the right of the Volkswagen, and then you say the Mercedes is to the right of the Volkswagen. You have this question, then you could put it outside, or you could insert it between the Audi and the Volkswagen, right? And then there's a systematic tendency that people will not disturb the map they already have. They put it outside. And when you then ask, where is the Mercedes relative to that other thing, which I don't, maybe was it the Audi? Then they will actually say it's to the right of that. And that's a way to probe that. And so that's the general theme where we're also interested in that. And that actually it has a very deep meaning because if you reason logically, that would mean that you are able to operate with these abstract concepts, and you can really know what is true about them, which neurally is really very challenging to think of how you could do that. Well, if you do this with this grounding, then the only way you need to know about spatial relations, for instance, is really in the grounded domain, where we do that for perceptual grounding. And so you can then lift that to do it with tasks like that. That would be a very general hypothesis. So when you ask people, give them little puzzles like that, they often do things that are not logically correct, because they often add assumptions that are real-world assumptions. For instance, one of the examples Johnson Laird used is something about a waiter, an Italian waiter that does something, and then a French waiter. And so you have to logically analyze who did what. And they all assume that the French waiter and the Italian waiter can't be the same person, because they're assuming that a person has a unique nationality, which wasn't logically given, and it's actually not rigorously true, right? And that is an example of people using more information than formally present, right? And people think that's errors of logic, but this actually reflects really how they do those things. Anyway, so that's the data that we're based on, and this is the model for that. And you see, the model it's the same model as I just showed you. It's a bit simplified. It has only spatial relations. It just doesn't have visual input. So it has actually the picture. Unfortunately, is, I think the architecture we published, we flipped it in the horizontal, right? These feature space fields were on the left, and now they're on the right, right? If I go back to this model here. See, this is the feature space. They get the input from the scene, right? And then we have the nodes here, the coordinates is formed, and the spatial nodes, and it's now flipped. Everything is on the left, right flipped. Then it's the same model, except a few nodes less. And here's the spatial nodes. Here's the color nodes, and there's the feature space fields, and here are the coordinate transforms, right? And so the difference is we don't get the input from the visual array. Instead, we have a spatial map here. This will be the mental map, where we built a map, and we built it by activating phrases. So these nodes will be activated, and we're inducing peaks ultimately here at this bottom field, where we're the relational field. I showed you previously how we can do that. So the only thing is we need to start with something. So the first object that is mentioned, the red, let's say red target, is just put into the center of that map, and that will sort of automatically, there is some bias to be in the middle. If you just boost the field, the peak will be formed in the middle through some asymmetry, some boundary effect, which is not so important. And so the first object will be in the center, and now if you say something to the right of that, then it's put on the right, and so on. And the fact, so actually I have these amplified here. In fact, I think, yeah, this figure is actually enough to say that. So here, for instance, a few peaks have already been built here into this scene representation. And if you add something, you see that like this was something to the left of some reference object. And you see here this little inhibition, that's objects that are already there. They will have an inhibitory influence. It's kind of automatic through the way this is built. And that will actually make that regularity, that is, if you add a new object, it will not so easily squeeze in here before. It will tend to be on the outside. That's how we sort of account for that effect. And it's really emergent. It's not something that we could do otherwise in the models. In that sense, it's a kind of strong account. And so that can do this kind of task. So for instance, this is the model when it's already built the map for these objects. We label these here just for us, right? It's in each case, what is there is represented by the fact that in this feature stack, there is a color associated with that location. And it gets a new phrase like blue to the right of red. And it puts, in fact, this is exactly the case I'm talking about, because here green is already to the right of red, and you're getting blue to the right of red. And now you're inserting it on the outside rather than in between. And that happens here in this reference field, you know, in the target centered on reference. So somewhere here, see, exactly here, it happens here. Now you're through this phrase, this is the reference, you know, the target is represented relative to that, and now your kernel will bring up something here in this half, and it doesn't come up here, it comes a little bit further to the right. That's where it comes up, right? And then you can do inference. Now, once you have this map, when you now ask, you know, where is blue relative to green, for instance, you can do the same thing that you did for perception. Right? This doesn't matter now. The neural representation is the same. You can just use the regular. This would be a description, actually. You specify objects and then describe the relation, generate the conceptual representation of the relation. That's how you give the answer. That will be inference. Yes.
Yes, like people add extra information there, which is not actually there. So, like logically speaking, there is no unique answer.
Yes, exactly. Yes.
To this question, but people tend to give the answer, and the model does it in the same way.
Yeah, exactly. And in the model, it would be difficult to do it another way. Let's put it this way. It's in a bit of a structural. I'm not saying it's a real prediction, because these are, you know, I wonder if we can say rigorous, but it's certainly very plausible that this rule would arise, because it would be hard to do it the other way. There, unfortunately, again, this is a domain where there is some psychophysics which consists of things like that, but somewhat qualitative. And there's another line of work where, again, where they built multiple maps. So where there are multiple ways of possibly mapping, and in fact, there's something where you could have some objects form one map, and some other objects are not connected to that. So if you talk about, let's say you have German brands and French brands, let's say, just to make it easy to, and you find out that they're never really related. So they are like two maps that are not really related. And then you kind of connect these two maps, and that's hard for people. And then they will just make errors. And that's something that we can model, even though, well, I would say only in the sense we can, but it's not really, it just shows that it has also problems, let's say. There's something we're currently interested in, how to build multiple maps, and this plays a role in, goes a little bit too far, but for instance, binding through ordinal dimension is a current topic. You probably haven't heard about that. This is a hot topic right now, where you can say, just because things happened at the same time, they are somehow linked. Previously said we were binding through space, so that all the properties of an object you bind together. But you can also, in the laboratory, you can do this by showing an object at a location and then extinguishing and showing another object. It's not very naturalistic, and usually that doesn't happen, but you can do that. And then you can also bind these things together, even though they're all the same spatial location, so you can't use space. But somehow you use time, the ordinate dimension, right? And that is, I think, related to the fact that you have different, actually in your mind, you have multiple different scenes. I always use this example of a book, right? You have a notebook in front of you, and you may know that on the top left is the date, let's say, or you wrote something on the top left of that page. And that you will know that independent of where that book exactly is. Right? And on the other hand, you know, on the table, there are these cables here on the right, right? And that's just other reference frame. And maybe the door, the room, and Bochum, and there's a different reference frame like that you can keep track of. And there you can't really use space alone because you have to still know which space. And the example I'm talking about is a degenerate one because on the computer, they just superpose these on top of each other. It looks like the same space, but it's actually different scenes that at different moments in time, different things came up. So if one of the objects was shown with a context, like a whole book, and then you show another book, like when you use PDFs, right, then you have that problem, sometimes different documents. And then for each document, you would have a frame where, you know, in this PDF on the left top is the logo of the newspaper and stuff like that. So that is something that probably plays a role in these things, that you have multiple, not just one map, you can make multiple maps, probably a limited number. And there will be probably some errors when you have more than 4 probably, or 3 or something. And so that will be another source of constraints. So I'm going way too far in my speculations. Yes?
Sentences more, for example, the blue above the red, but to the right of the green, and below the yellow and stuff like that.
Exactly, yes. Actually, I did have this plan. I should show that. And just have patience for one more thing. Could show that. Yeah, I just want to say that, yeah, I'll explain next week the sequencing in here. So it's this sort of thing I think you're talking about. There's a possibility that your brain is full, but let's say just put it here and then we can take that up again next week. Next week actually doesn't take so long, so we can discuss it a little bit. So that is, so in nested phrases, again, these phrases, Daniel Sabinas's work is that he will defend his PhD in a few weeks. I always had to fight to make the phrases not too complicated, because then they become really not very naturalistic, which is an interesting debate because of the tradition in cognitive linguistics talk about recurrence, and infinitely recurrent. It's total nonsense. You can only recur maybe 2 sentences. And if it's more than that, it's more like problem solving. Like if you read Kant, you have to really take notes to understand the sentence. It's not really natural language. So you have a sentence like the tree to the right of the tree that is below the lake and above the house, right? He thinks that's a natural thing. Okay, you need if you look at this scene, it takes some time to figure out which tree we're talking about, right? So it's actually this tree we're talking about. So the right of that tree that's above the house and below the lake. Okay, so the color code, actually the green, I have to use the color code even to remember. So this is an example, so it's a nested phrase, right? And it's an example that is chosen carefully because it has the so-called problem of 2. That is, you have 2 trees that are different tokens, of the category tree, and you have to realize that they are 2 different ones, and then also in the grounding, right? That they are separately grounded. And therefore, you also have to have a way of knowing that the relation to write off, takes this tree as the target and that tree as the reference, and then this tree is the target of that relation. It's sometimes called the problem of 2, how to keep track of different tokens. And that's not a problem in information processing, symbol manipulation, because symbols are exactly like that. You create a token of a symbol, right? And then you give it as an argument to a function, relations of functions that take two arguments, it's all very easy. But neurally, that's a problem. And can you just put out another neuron, or how do you make that now? This neuron is an instance of a category. We have only one neuron for a category. How do we do that? And so that's actually unsolved as a problem. It's a really big, and there are proposals, and we believe we make the best proposal here. So we're separating we deal with the problem of through binding, introducing a binding dimension. That is, we're proposing that every object or property concept has a hidden dimension. We call it index dimension. Unfortunately, it's a bad name. It's actually an ordinal dimension, so that you can talk about the tree as the first thing we talked about, or the tree as the second thing we talked about. So it's actually concretely, we're building right now a model like that, concretely the idea that when you process things like that, so language processing will not model because it's another field, but the visual property, if you describe, right, you will be looking at a tree and there will be a counter that keeps track of the first thing you do, the second thing you do, and the third thing you do. And that counter is actually the sequence generation mechanism I'll talk about next week. It's ordinal, called ordinal dimension. So that gives us activation along this axis. It's actually categorical. It has only 4 slots, we presume. But it has a field-like property in the sense they're all competing. You can only select one at a time and so on. And in fact, these dimensions are shared, and so you can put in ridges, right? And it has the same logic as a real dimension. So when you do that, you can solve the problem of 2 by representing the 2 variants of tree as through different ordinal moments. So ordinal in the sense it's temporal, but just categorical temporal, who comes first, serial order, right? Serial order index of these 2 trees. And the same actually we postulate for the relations. So that's why with the little indices here, that is every relation, these are the relations like left, right, above, and below. And we're assuming that these nodes for the relations also have a dimensions different index, the first relation. So this is why the write-off has an index and so on. So that would allow us, the phrase isn't like that, it would allow us to have 2 write-offs. You could easily say, the tree that's to the right of the Volvo, that is to the right of our house. There would be 2 different to the write-offs that take different arguments. And so when you have that, you can do the role-filler binding in a much more interesting way. Because now you would say, okay, there's a target and a reference field. I call them fields, even though they have these discrete nodes. And these fields are only in the index space. That is, I have relation number 1 has as a target object number 1 and as a reference object number 2. That's this here, right? And relation number 2 has, object number 3 and object number, what is it? Object number 2 and object number 3 as an argument, and so on. And so that's very attractive because that solves a famous problem. If you had, so this is this problem of how to attach the arguments to the relations, and it would be true for all verb-like things, actions and so on. And so if you had, so if you were to attach these roles to every relation and every possible argument, you would have to have a lot of neurons. You can actually think now for every neuron, you would have to have a way of how to represent it as part of this relation or as part of that relation, and so on. I mean, imagine. In fact, the competing model is called Lisa, and there's a variant called Dora. It's an acronym for something. And they really postulate that. They assume there is a neuron for the ball as something that's being caught, or the ball that is rolling, or the ball, all possible things that a ball can do. It has a neuron to express that. And they say, it's a bit of a problem, but then I have some arguments, well, maybe only 1 million or maybe only 2 million possibilities. But of course, it's not true, because we can actually expand that all the time. We can build new relations and build new language elements like that. And so this is not like that, right? Here you would have a very limited set like this. This would be a couple hundred neurons perhaps, and it would it's through the indices that it gets contents. So that's attractive. But now we have to worry about, but can we still ground? I mean, is it now an abstract thing like symbols, or can it actually still be grounded? And it turns out it can, but there's some effort to do it. There's a subtle problem here with these indices in that they're all shared. And, you know, if you have a million concepts, you know, can you have a million synapses to the index dimension? That is probably not true, and that's a challenge. So there might be possibly there's some subdomains, and you're not everyone is connected to the same system and so on. So there's some open issues here. Yeah, so the grounding for that is complex. So it's these two graphs. So this is a little thing, and then that's here, and then there's all that. So that is not totally trivial. It does, however, have the same sort of thing. So these are these feature space fields. There are more here. These are the individual feature dimensions. There are also more here. There's a memory, so it's an attention and perception dimension of it, it's just different modes. The input, where's the input? Somewhere here. Oh, yeah, here the input goes, this is the input, very tiny little thing. And then the feature extraction goes into those things. This is these nerds. If I can go very amplify, and there's a real photograph from the simulator in here. And you're already familiar with that. We're building actually a mental map, the generalization of the previous mental map. You know, previously, this wasn't really quite so plausible that we have for every, you know, with the red, it didn't show up so much. But if you now think you have really a mental map for Mercedes, or you could do this for people, you say, Erica stands to the left of Ingrid and so on, right? And do you have a spatial map for every concept like that, right? That's not possible. And so that's where the index comes in, right? You could say the first thing I talked about is at that location. The second thing I talked about is at that location. And what you need is some ability to then again say what the first thing was. And that's what this machinery is about. Yes.
Here's like the person map, and there's like Erica activates, and the other guy activates, like she activates the target, and he activates as a reference.
Yes.
And then there is like relation map which activates, and then at the end we have this Erica steps.
Yeah. So if I took the thing we did here, it's a little bit cheating in that we have the spatial map, and the contents of the map is in the feature space, right? We know that this is the red and that is the blue because it has to peak in the corresponding level of the feature space. But that means that this is a way of doing mental imaging only for things where we have the corresponding feature map. And we have some feature maps. But most of the use of maps will be categorical, right? When we think about Erica and Ingrid, let's say, and therefore, do we have a 3D map where is Erica here and Ingrid there, and has a whole spatial field, so neurons that are tuned to Erica for any location? That's not possible. It would not scale well. And so that's sort of a bit hidden problem here. And with the index, this becomes much better, because with the index, we would say there's only one map like that, actually maybe two or three, and they are about ordinal. So I just keep a track of where things are that I attended to, and I keep track of the order in which I attended to it. And then I also know what the category was that I attended to. I mean, in that order. And therefore, I can know that the first thing was Erica I attended to, and it's at that location. And now I have just one neural substrate for that. Yeah.
Okay. Shapes altogether they constitute Erica. Then we know that it's Erica, and then we look at this relational map.
Yeah. Yeah. So I mean, it requires a bit more careful explanation, but it would be the idea that this would be your universal map where you just know the first thing I did, or I'm interested in, is here, and the second thing is here. And so you have one neural, it's like a hippocampal map, right? Where you have different places, and the different places are, you know where they are. And you also have some count, like this, the first place, the second place, the third place. And then the other thing that you need is some representation where a object, I have to look where it is, like here, where you know that the ball was the first thing I attended to, and the tree was the first thing I attended to, the second thing, and so on. And so if you're now saying, oh, where is the tree? You say the tree was the first thing, or the second thing, let's say, and the second thing was at that location. And that's how you can now actually effectively have a map of the tree over space without having neurons that are tuned to trees with a receptive field. Even though Raul, my colleague, always argues that everything has a little bit of spatial tuning, so it could be used for some things, but it's certainly, this is much more universal. That's why being able to show that it's still can do grounding is a critical step, because it sounds like a fairly abstract computational thing, and we just have to make sure that we didn't lose the properties of sensory motor grounding.
As I said, we have talked about two indexes, and then referring through that index for the content, what is stated to it.
Yes.
Done by working memory.
Yeah. So that's what we're assuming, that it's in working memory, and that is part of the capacity limit of this. And when you do these things, the grounding of things like that, that is one of your constraints. In fact, this is already pushing the limits. And I think if you have spoken language like that, you will probably not really know. And we had a lot of debate about that. So when you're doing this with written language, I always mention Kant. If any of you ever try to read Kant, you will see this is crazy. I guess, maybe nested like 5 deep. So this is really more like math, where you essentially you need paper. What is paper? It's just a spatial map that you have a perceptual representation of. So extending your mind, right? The philosophers make a big fuss about that. So you're making it possible to do that with normal perceptual grounding, right? By having that piece of paper where you mark it down, and that simplifies, and then you actually have to attend to that again. There's some limitations through that. You quickly get to a situation where that working memory, also a whole topic. Working memory always also builds long-term memory. It's just a question of consolidation, whether you keep it or not. And so it's not always clear that you will have it all activated. That is, you might be able to reactivate it from a memory trace, for instance. And there are actually variants of this model where we do that, where we build a memory trace. The intentional architecture I showed in the last lecture actually has that, builds in the C memory, and it also puts in long-term memory. So you don't have to have it activate all the time, and then you can recall from long-term memory. But that's a whole other topic, because long-term memory, is it what its properties are. But in first approximation, it's all working, and that limits what you can do.
Do you think that we talked about how this visual search is then going against bottom-up salience? It's likely that there's some kind of dopaminergic influence somewhere on this, yes? Where do you think this influence
drawn to these
direct?
mechanistic questions?
Yeah.
Yeah.
Sorry.
So the neural substrate for that, right? So we certainly know, again, these are these islands of knowledge. I talked about that yesterday in the other lecture, right?
Yes, of course.
So, the problem is the way people, for instance, talk about dopamine comes, of course, from certain kind of experiments. Many of them are conditioning kind of experiments. And then you can sort of take this label, that it mediates learning, for instance, and then extrapolate that and say, in any other context, whenever something learning like happens, it must be dopamine that mediates that. And the truth is, we don't really know. And it's quite possible.
I wasn't talking about learning. I was talking about attention. And we know that people with dopaminergic deficits, specifically in ADHD, have problems with attention. Like they're more subject to, the bias seems to be salient towards salience.
I see why you say that. Yeah, so I would say this has to do with inhibition, and dopamine does contribute to that. So it's one of the vectors of how to do that. the direct interpretation, these kind of interpretations are always problematic. We talked about that yesterday in person,
Yeah,
right?
of course.
Because you could have that when you have a deficit like that, yes, maybe your excitatory inhibitory balance is not right, and that could manifest itself in many ways. And that lack of inhibition might show up. It will really be hard to say, that means that the dopamine is doing that thing, right? As I mentioned yesterday, when the Breitenberg vehicle, goes in circles, doesn't mean that the thing was suppressed is the straightening agent. It is just some manifestation of this unbalance that is there. And one can say generally, this ADHD, for instance, it has a general signature of being less able to stabilize certain kinds of representation. We typically think of them like goal or task representations. And that might manifest itself in many sub-aspects of tasks. And it's quite possible that in a task like that, they would also have a deficit that could have to do with that. I'm not saying it's useless knowledge, but it's very global, right? It's just this, you got to have the right balance of excitation and inhibition. So
I'm just basically wondering whether the problem would be more likely to originate from a problem with stimulation of the top-down system, or with the problem of the inhibition of the bottom-up system. Both are possible, but just curious.
You have these. So most people model these things don't really have function models. That is, they can't really show how that particular model supports a reading or some visual task or so. And I think if one had function models like that, it might be easier to make really such functional sense of things like that. I'm sure it's a complicated phenomenology where I'm not confident that a simple account like ours would be sufficient, but one could try that.
Cool.
It might be an interesting way to do that. We have one program where we took these kind of models, also somewhat complex models, for cognitive control. It's like 10 different tasks. People had to like a go no-go task and Wisconsin card sorting task, and I think like assignment task, couple of things. So really concretely had people do that, children and adults, do all these different tasks, and then we recorded them in the fMRI machine. And then we had a complex model that models all these tasks in one big model, and that we use then as a regressor for the fMRI machine. And so that gave us a sense a little bit of that. I mean, the kind of thing we did was, this big claim is that we were able to really predict differences in the bolt signal on error trials versus non-error trials, which is very, very cool. And you have to have enough errors, of course, to do that, which made functional sense in some way. And I would say from this kind of work, you're asking this sort of hardware question, I would say, and it's typical. In a sense, a lot of people, of course, very interested in that because we do have psychiatry, neuropsychology, and of course, this question: how does the brain do that? And so, in principle, approaches like I'm sketching could do that. The problem is, I call this the automechanic effect. So if you are a naive quantum science student, perhaps you have a car and it doesn't work, then you're puzzled. Why doesn't it work? It's awful. If you are a car mechanic and you know about a car in a lot of detail, you wonder why it actually works, because you know about so many ways of how it could not work. It's kind of amazing.
Yeah.
And I think that's sort of where we are. We know so many things about these models because we built brains, right, with these models. They're simple brains, and simple both in the functions are much simpler than our functions, and also the hardware is much simpler. We don't have spiking, we don't have problems with dopamine, whatever. We just have Amari fields that we're using have the inhibition folded into the excitation. It's automatically stable. There's no problem with inhibitory deficits. So it's much simplified. But when we build these models, we say, oh, how many ways this model can fail? This is until we get it to work. Right? And the CEDA exercise can give you a little bit of a sense for that. When you, even if you were able to do it yourself, see that a lot of extra stuff is in the parameter tuning, which means your brain being right. So that's where you are amazed how the brain actually works, because there could be so many ways it might not work. And that is actually true. And it is, psychiatric diseases are actually among the most prevalent in the world, right? If you look at how many people have heart disease and so on, problems of the nervous system are really a major source of disease. And that makes sense once you understand how subtle the brain is. And that also means there's a lot of knowledge in these processes that keep the brain functioning. We call this homeostasis, just a word for it, meaning that that everything is tuned right, so that you are taking your top down, but you're not totally blind to bottom up, and not dominated by bottom up and so on. So it's a constant tuning process that you change when stimuli change in the intensity and so on. And so that's part of the problem of answering these hardware questions, right? That it's not only that we don't know concretely, but we see how hard it would be to have an answer to that.
Yes, why I usually ask these questions is because some theories they cannot answer the question, but they can sometimes exclude certain areas that might not be of relevance. Which,
Yes,
something,
yeah,
but
sure. Yeah.
Thank you anyway. I think
just
thinking about it really helps me work smoothly.
Yeah. Good. Maybe this last thing, I just wanted to show this video. So this is the process model running like that. So it gets this input, and it is ultimately in the mental map. We put little numbers here. It's building the mental map by attending to different objects at different time, making sense of these phrases. And then in the end, the answer should be this object, which would be in the attention map, should be here, I believe. And it would show up also here. And yeah, so these are the three ones that were mentioned that it maps. And I think then in the end, it finds here, it's found the target of this phrase, right? And I can't explain exactly how it works. I mean, and it just shows that you can do that. And the next and conceptually, actually, the final topic in this course will be next week to understand how the sequencing happens. We'll not understand in detail for this model, but we understand the principle of it. And then we have the raw ingredients to understand higher cognition. It's kind of amazing. Good. So this is currently ongoing research. So it's clearly this is the more speculative part of the course, and I'm also not really expecting you to necessarily believe it all or buy into it, but it's just stimulation in which direction that goes. Good. So I'll close here.